Morning, people. Can you hear me okay? Somebody acknowledge, please.
Yep, can hear you.
Thank you, Derek. What do we have? Only 13 people. That's fantastic. They dropped like flies, apparently. 14. Well, maybe we better wait a few minutes. 15, 16. That's good. We'll wait about 5 minutes just to make sure everybody's on board. I know that there must have been a significant drop in numbers because the wait list all of a sudden shrank suddenly. So I guess a lot of people just don't care enough to put in a bit of extra effort to learn something actually quite exciting here. What do we have now? How many people are here now? Let's have a look. Not very many. Might be a disaster, huh? "17 people. That's not good.
I think it's not updated.
I see 56 on my end.
56?
See 57 now.
There's 57.
Why do I only see 18? How about that? Okay, never mind. Let's just get started. Thank you for that. All right. What are you looking at to see the numbers?
The bottom bar.
I was looking at the wrong. Oh, I see there. Okay, yeah, 57. I see it too. That's a healthy number. Was 115 though. All right, let's get started. There's a few things that I need to say. Yesterday for 376, there was some sound problems. I'd say about 20% of the class really couldn't hear very much. And I think that's because there was problems with Zoom. There was a technical problem with Zoom. Hopefully that's fixed. If you are having trouble hearing me or having trouble with the video or anything, please send me an email after the class. There's nothing I can do about it right now, but I just, need to monitor this problem just to make sure that it doesn't continue. Okay? So if you're having trouble hearing, seeing these lectures, shoot me an email at the end of this lecture, please. Okay? All right. So that's one thing. Also, pretty soon the record feature for Zoom will be available. And I just don't want to increase the bandwidth because recording really puts a big burden if everybody's doing it. But I suppose I'll do it. You're all already welcome to record them on your own desktop, like I said. As far as I'm concerned, Zoom office hours are much more effective than recording lectures. And also, I'm going to tell you I'm not part of this movement to move teaching online. I'm completely against it. And I think that a lot of people are going to use this as an excuse, and students are going to be the big losers here. Education is face-to-face. There's never been one demonstration that technology has actually improved education, and I can give you references for that. Call me a Luddite. Also, the mathematics appears to be fairly intimidating, wouldn't you say, some of you people? What do you think?
Yes, I agree.
Okay, I am not kidding. Bear with it. Next week we do the math, and I'll show you exactly what to do. All of your mathematics problems come with solutions. And so I want you to understand how they're done. I'll even pick out specifically the stuff that you're required to do. You've got 24-hour take-home midterm and final. Don't worry about it. As long as you understand it. As long as you understand it, that's what we'll spend time doing. So I'm really giving you guys a real break on that. Okay, does that seem fair?
Yep.
Okay, that's because, yes? Okay, so, all right, and are there any other concerns at this point before we get into this long PowerPoint? Anything at all? All right. Okay, so, yes?
No, I'm just saying all good.
Oh, okay, all right. Sorry about that. So let's just get going. I mean, I'm going to go through this quickly because I know you've all actually looked at it, all 66 of you. There's this whole business about quantum physics that's very different from any direct experience that we have here, at standard temperature and pressure in the macroscopic world on a terrestrial planet. You see what I'm saying? And things down there, we have no direct experience. but it is the way nature is, and therefore we have a hard time reconciling with it. Also, information theory is closely tied to thermodynamics. Who has not had any thermodynamics? High school physics, I think you all have, yes? I hope you have. And so the concept of entropy, the second law of thermodynamics, is very, very closely tied with information. In fact, it's called Shannon entropy. Hopefully you've all heard of Claude Shannon, the seminal 1940s paper on basically information transmission. And so that has to do with reversibility. We need to deal with quantum circuits that are reversible, because quantum mechanics is reversible. And that means that any gate that you come up with is going to be a bijection. That means, or a one-to-one correspondence. It's both onto and one-to-one, okay? Then we'll be talking about the bit versus the qubit, introducing these things. A qubit is a quantum bit, pairing, contrasting classical computing with quantum computing. We'll talk about the mathematics in short form, and then describe the basic postulates of quantum mechanics, which I will show in very simplified form in the end, after showing you sort of everything, what we need for quantum computing. So here, this is the first week's notes, and that just simply means today, basically. Don't forget, we have week 5 or 6, is it? There's Slack week, right? That means, no, week 5 is Slack week, so we can actually stretch this stuff out a bit. We talked about this already, chapters 1 and 2, and a bit of chapter 3, or what we're going to cover here. Chapter 2, I don't care if you read that in any detail, because it's about, the history of quantum computing, which is not imperative. But you'll notice it's all based on this one PowerPoint this week. And then next week, we'll have this Mathematical Foundations PowerPoint, which is part 3 of your textbook here. Oops, sorry about that. Oh, come on now, you silly thing. So, for example, we're talking about the first, 3 chapters, roughly. A bit of chapter 3 will be discussed here from your textbook. And then when we go to the mathematics, I'm going to go to Nielsen and Chang, the third book in your administrative PowerPoint, and just section 2.1, which I emailed out to you on Tuesday, along with the answers for all of the problems. There's some roughly 50 problems in section 2.1. And believe me, you don't have to look at all of them. We'll get through it. I'll clear it up for you. Don't freak out. Just stay with me. I'll show you what to do. And of all of these week 1 PowerPoints, those are all videos. I don't really want to spend time watching them here. You can do that on your own. The links are given. And here, this is the practical quantum instruction set architecture by the software engineer from Rigetti, which is one of the big quantum computing companies. And that is, remember, the goal of this course is to be able to read that, one of the 3 goals. That's the PowerPoint that we're going to be looking at. And here I've just sent out these. I haven't sent this one out. I've sent out these 3 papers for you to look at just now. That you don't have to really know Bell's theorem, so I'm not going to send it to you. And notice that it says R. Anytime there's a capital R on anything I send out, that means it's just a reference only. And so you're not responsible for it. Okay, so one big long PowerPoint and several small readings in PDF format. And so again, these are our 3 primary goals. One is basically the goal of this course is quantum algorithms. And so we'd like you to be able to write a simple algorithm by the end of this course. Understanding them is one thing, writing them is pretty trivial. When you see the kind of Python-based pseudo assembly code that you'll be using. And in fact, that's what this paper is about, a practical quantum instruction set architecture using PyQuil, okay? PyQuil is one of these Python-based, the PY part, second generation, pseudo second generation languages. When I mean second generation language, the way we described assembly many, many years ago. QS gets another version. That's from IBM, okay? And then finally, you got to be good at the math, and we'll do that next week. So those are our goals. Basically, this is my philosophy here. It's a quantum algorithms course. It's not a physics course. It's quantum algorithms, but it is based on quantum mechanics. And so it'll be the most physics intensive course you'll take in this department, no doubt about it, as a pioneering program with physics develops. And the whole point of quantum computing is to take advantage of these very bizarre aspects, these extraordinary, non-intuitive aspects of the quantum world. So what are they? Let's have a look. First of all, I'm sure you've all heard of the double slit experiment. It's famous in physics. It's the starting point for a lot of people in learning quantum mechanics. Double slit experiment. Basically, I've got particles coming out here. You know, you can think of light as a stream of particles or a stream of wave or a bunch of wave fronts. I'm sure you've heard that both interpretations make sense. What does that mean? Well, let's think about it. What if instead we're shooting electrons through here? I mean, most people agree that electrons are particles. Most people. And so if you're going to shoot electrons through this double slit apparatus, you expect to see this simple two-stripe pattern on the screen. But instead, what you see is this, an interference pattern, much like the interference pattern produced by two sources of wave fronts, circular wave fronts coming out of two sources here. Okay? And that makes no sense, really, when you think about it. You see, this is why I don't like these are actually probability waves, as we'll see. And they're a different kind of probability. It isn't just the normal probability from, well, of just simple additivity. It actually involves constructive and destructive interference. And the square of these, the so-called probability wave, is what gives you the actual probability distribution. We'll get to that. And so what I'm trying to say is that probability of this distribution right here comes from this interference pattern produced somehow by these particles or waves going through those two slits. And if you want to find out, is it a particle? How would a particle go through one slit and the other at the same time? That just makes no sense. And if you try to put sensors or detectors out to try and determine which slit an electron went through, all of a sudden it doesn't behave like a wave anymore. It'll just form this pattern. So that's pretty strange. There's a lot of bizarre aspects that we don't really fully understand, but the mathematics is incredibly precise. So let's just continue. Our first question is, particle or wave? Okay. And to say it behaves like a particle and a wave, that's fine. But to say that it is a particle and a wave at the same time is not fine. Okay, so it's just behavior we're talking about. And as a side note, the advanced theorizing beyond quantum mechanics is called quantum field theory. It was developed by Richard Feynman and others from Caltech. And that is where you actually reconcile with this particle wave duality. And so let's just leave that alone. There's no need to go there. So there's another thing too. You've all heard of superposition. The superposition of linear wave theory is pretty straightforward. It just basically tells you, well, you know, I mean, you've all seen, let's see, I'm going to do something. No, let's just keep going. Let's just keep going. No, I'm going to do it. I'm going to show you something. Let's do this. Let's do this. Give me 1 second. Give me a second. Give me a second. Okay, let's do it again now. Dum, dum, dum. So, for example, this is from Wikipedia. You see these parallel waves coming into the shore, moving, I guess, to the upper right. And then the wake of these ducks is producing a more complex pattern. It's actually a wave pattern, an airy wave pattern. But they're additive. The superposition principle has to do with, you know, the principle of homogeneity, for one. And can you still see this right here? I just went back. You can still see this, right?
Yes.
Okay. And
Yep.
so these two properties of a mathematical function is what defines the superposition principle. And in quantum mechanics, this holds. So we have linear waves in the study of quantum mechanics. So that's all we really mean. Let's go back to this thing now. Nope, that's not right here. Okay, can you all see the PowerPoint again?
Yes.
Oh, yes, Connor, please.
Correct me if I'm wrong, but are those additivity and homogeneity, are those not exactly the same? Shoot, I'm missing the word. Exactly the same things you see for a linear function in linear algebra?
Absolutely, absolutely. It's the same thing. In
Okay,
fact,
great.
I'm glad you said that because when we say superposition in quantum mechanics, all we mean is linear combinations. So
Right.
you're right.
Okay, thank you.
That's great. Yes, thank you. Okay, so how many people get the reference of these two cats? I'm sure you've all seen, yes, Schrodinger's cat. I'm sure you've all heard of it or seen some reference to it. We'll talk about that later. But the whole point is, before you measure one of these subatomic particles, like for example, an electron, you don't know exactly what state it's in. You just know that it's in a superposition of states. And that superposition it describes a probability of being able to find it. And it's completely different from the classical world, where you really know the trajectory and momentum and position of particles. In the subatomic realm, you don't. You only have a probability of being able to find something, and when you actually try to measure it, that's when you've probably heard of this phrase, the wave function collapses, and it goes from quantum to classical. We don't know what that means, but we don't have to in quantum computing. We just want to exploit this because superposition, if you can actually exploit it for computing, greatly enhances the power of the qubit, which is the quantum analog of a bit. And we'll get to that. The other thing too is, if I can just get back to this, is this idea of, see, there's the probability distribution of seeing, of determining where a quantum particle is. We call that the wave function. We'll get to this in a minute. But when you measure it, the wave function, quote, collapses. And so there's a point particle somewhere in space-time. Here, it's a probability distribution or a smudge. And what this active measurement is, some people have taken way too far and said, you need to have a conscious entity in order to observe the universe. Just forget all that stuff. Simply what's going on here is we don't have a complete theory, but the quantitative aspect of it is completely accurate and unprecedentedly successful. The reason why I'm using this computer and the reason why you're using your computers, the reason why we have all the gadgets we have today is because of the success of quantum mechanics. Here's a strange one, though. This is a really strange one. So if we read it even stranger, widely separated physical systems can behave as if they depend on one another no matter the distance of separation, right? As if they're entangled by what Einstein called spooky action at a distance. Action at a distance is a term that came from Isaac Newton in the 1600s, where he developed his, theory of classical mechanics, as we refer to it now. But he was so unsatisfied with it, as were a lot of his colleagues, because he still didn't know what gravity was. I mean, you can describe it with Newton's fourth law, but what is it, right? And so they called it action at a distance, for lack of any better term. Now, Einstein took that ahead and said, this quantum effect called entanglement, which he didn't believe in, that's called spooky action at a distance. So not only is Schrodinger's cat an attempt to make a fool of the theory, to show the theory can't be right, but Einstein's spooky action at distance was as well one of these sarcastic, little stories, and hence research studies to prove that our interpretation of quantum mechanics isn't correct. The funny thing is, it is, and we'll get to that. That's the funny part of it. And so basically, these two particles can be correlated in such a way, super correlated, that is, that if you determine the state of two entangled particles that are separated on both sides of the universe, by looking at this particle here, its wave function collapses, it's say spin down, or it's left or horizontally polarized. The other one on the other side of the universe, you know immediately what it is. It doesn't mean you have information transfer. We'll get to that as well. And believe it or not, an experiment has recently been done that verifies this as true from photons that were emitted billions of years ago near the Big Bang. It's an amazing experiment. And they showed that this effect is actually true on such cosmological distance scales. Interested, people? It's kind of cool, isn't it? Just say yes.
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 All right, let's keep going. So all we've got here is, okay, we have a theory that has, like all theories, a mathematical aspect, hopefully, and a conceptual aspect, you know, at least in the realm of physics. That's why I'd like to stop and say for a second, that's where biology is weak as a science, because it really hasn't developed to the point where it's very quantitative. In fact, there's a lot of problems with biology, though it is all we have right now as far as a scientific theory of species and life forms. But let's not get into that. In physics, the easy stuff is physics, because we're looking at simple, small, isolated particles, the simplest, most fundamental building blocks of nature and so forth. But yes, the mathematical part is unbelievably successful. The success of the theory is exemplified by solid state physics and all our technological and microelectronics revolution. But on the other hand, there's nothing but debate about the actual interpretation of quantum mechanics. And this is a very nice paper you can go to. It says FYI, that means for your information. You would never be tested on anything that says FYI, all right? You already know that. You can go there. It's by a current famous Caltech physicist, and we'll leave it at that. So this, on the other hand, I'm going to start showing you a little bit of, if you don't mind. Can I do that for you? Give you a break from my monotonous, boring voice.
Go for it.
All right, man, you're all right. Okay, what am I
I
supposed
would normally be giving a thumbs up, but
Oh,
hard to do.
gotcha. Hold on. There we go. Okay. No, that didn't work too well. Just a second here. Let's see. I can do this. I have the technology. Share screen. Go. Can you see that?
Video was sponsored by Norton 360.
Classical mechanics is great. If you know the state of a system, say the position and velocity of a particle, then you can use an equation, Newton's second law, to calculate what that particle will do.
Can you all hear that okay?
All good?
Yep.
In quantum mechanics, if you know the quantum state of a particle, that is, its wave function, you can use the Schrödinger equation to calculate what that particle will do in the future.
By the way, you're not required to know calculus for this course. Clearly, this is a partial differential equation. We'll be talking about it, but you're not responsible for even regurgitating it in any way. Just linear algebra.
Usually, it spreads out over time as it is doing here. Note, to make this animation, we really solved the Schrödinger equation. So there's a beautiful symmetry here. If you know the initial state, you can use an equation to evolve that state smoothly and continuously into the future. The problem is, in quantum mechanics, we never actually observe the wave function like this. Instead, when we measure it, we find the particle at a single point in space. So how are we to reconcile the spread out wave function evolving smoothly under the Schrödinger equation with this point-like particle detection? Now, I think it's understandable that when the founders of quantum theory approached this problem, they considered the measurement more real than the wave function. After all, the measurement was something we had actually observed, and it matches our experience of a world of matter particles. It was harder to say what the wave function was exactly. Schrödinger formulated his wave equation because scientists, notably de Broglie, suspected that matter has wave-like properties. But it took a third physicist, Max Born, to propose how we should interpret the wave function. At each point in space, the wave function has a complex amplitude, essentially just a real number plus an imaginary number. Max Born suggested if you take that amplitude and square it, you get the probability of finding the particle there. The fact that you have to square the amplitude actually appears as a last-minute footnote in Born's paper, but that is how probability was introduced into the core of our picture of reality. That's a pretty big philosophical leap. I mean, no longer is the universe deterministic. This made a lot of scientists, especially Einstein, uncomfortable. But the Born rule, as it is now called, remains at the heart of quantum mechanics because it is spectacularly successful at predicting the outcomes of experiments. So the way quantum mechanics came to be understood, and the way I learned it, is that there are two sets of rules. When you're not looking, the wave function simply evolves according to the Schrödinger equation, but when you are looking, when you make a measurement, the wave function collapses suddenly and irreversibly. And the probability of measuring any particular outcome is given by the amplitude of the wave function associated with that outcome squared. Now, Schrödinger himself hated this formulation, which is actually why he invented the famous Schrödinger's cat thought experiment. Put a cat in a box with a radioactive atom. Add a radiation detector that triggers the release of poisonous cyanide gas. Now, although it was only meant as a thought experiment, Schrödinger helpfully notes this device must be secured against direct interference by the cat. Anyway, the whole point of the experiment is to magnify the state of the atom up to the state of something macroscopic and tangible. He could have picked anything, it didn't have to be alive, but Schrödinger selected a cat. If the atom decays, the detector detects radiation, releases the poison, and the cat dies. If the atom doesn't decay, the detector doesn't detect radiation, poison is not released, and the cat remains alive. Since the state of the cat and detector apparatus are directly tied to the state of the atom, we say they are entangled. Where things get weird is that according to quantum mechanics, the state of the atom does not have to be either decayed or not decayed. Generally, it's in a superposition of both, decayed and not decayed at the same time, assuming no measurements have been made. This superposition state of the atom gets entangled with the detector, and then the cat. So after some time, the wave function of everything inside the box is in a superposition of the atom has not decayed, poison not released, cat alive state, and the atom has decayed, poison released, cat dead state. So according to quantum mechanics, the cat really is both alive and dead at the same time. Only when we open the box and make a measurement does the wave function collapse and the cat actually becomes either dead or alive. These days, Schrödinger's cat is often used as a way to show how weird quantum mechanics is. But that wasn't Schrödinger's point. He wanted to show that quantum mechanics, as formulated, was wrong. So, taking up Schrödinger's argument in this video, I want to show that there is a better way to think about Schrödinger's cat.
And that's all I'm going to watch right now for that. I urge you to finish watching this. That's got some great graphics and so forth. Has anybody ever studied quantum physics to the point knowing what the Copenhagen interpretation means? Anybody? No comment.
No.
No, okay. Well, you don't need to know it. But anyway, the Copenhagen interpretation is very bizarre. We're not going to be responsible for this here, but I just want you to know that it's the most popular of all of these things. If I actually, let me just switch this off now, get back to the PowerPoint. What happened to it? There it is right there. So if you go back, for example, to, wrong way. If you go back to, if you, where am I? What am I doing right here? Never mind. Oh yes, there. If you go to this link down here, basically a lot of people today, they're trying to make sense of quantum mechanics in a common sense way, i.e. causal determinism. rather than just pure chance, randomness, and all that. And so these days, the many worlds hypothesis, you probably heard of that the universe is constantly, with every event, forking into parallel, slightly different universes. I don't want to get into that, but that's what this is about. I just basically, this is for introducing the ideas of quantum physics. And I thought that video was excellent in terms of how they showed the progression of the wave function by solving the Schrodinger equation. And but yet we don't really know what the collapse of the wave function means. That's all I'm trying to get across here, and a good historical account of Schrodinger's cat and how it's one of those things that was intended to show preposterousness, and instead, hey, it's true, it's real, and it's weird. Okay, people? So that's something you can finish watching. And they talk about superposition, entanglement, and the idea of measurement in quantum physics. Very important for what we're doing. Here's a fella, one of the most famous physicists of the 20th century, Richard Feynman, of course, from Caltech, the center of physics in the world, still to this day. And here you always hear statements like this. You can read that if you like. You can read that if you like, okay? You're not going to understand it. Nobody understands it. I'm not sure how helpful that type of thing is. And there's a guy called Merman, another famous person, with the most famous statement in quantum mechanics there is. Shut up and calculate. What? That means don't try and figure it out. It works. And that's what we're going to do. You can watch these videos. These green icons mean, you don't have to, okay? But if you're interested in the philosophical implications of quantum mechanics, these are excellent videos. And in particular, the pilot wave one. This is really cool. It is so cool that I'm going to show you a bit of it right now. You guys don't mind, do you? Just say I don't mind. Hello?
I don't mind.
Go for it.
There we go. Right. All right, because we want to have fun in this course, don't we? Okay, just hold on. Oh, you son of a... All right. Okay. Yeah, check this out, baby. All right, here we go. Okay. You. How many people have seen this?
Out. I'm using this speaker to vibrate a petri dish containing silicon oil. Now, if I take this toothpick and I make a little droplet on the surface, the droplet will stay there, hovering above the surface. The droplet is actually bouncing, and it'll keep bouncing for a very long time. Now, the reason for this is there's a little layer of air between the droplet and the surface, and the droplet's bouncing so rapidly that that layer never shrinks to about 100 nanometers, which is what it would take for the droplet to recombine with the oil. Now, every time the droplet lands on the surface, it creates a wave. But this is a special type of wave, driven by the vibration of the oil bath. It is a standing wave, meaning that it's not traveling out, it's just oscillating up and down. So the droplet makes the wave, and then it interacts with that wave on its next bounce. If the drop lands on one side of the wave, it is pushed forwards. And as long as the bounce of the droplet remains synchronized with the wave, it'll keep landing on the front side of the wave and getting pushed farther forwards.
Everybody get the idea where this is headed? This is an interpretation, actually goes all the way back to de Broglie in the 1930s, I believe, to come up with an interpretation of quantum physics that makes sense in a deterministic kind of way, a cause and effect way. So you can see you have both the idea of a particle with the droplet and a wave, the wave that the particle is producing. Never mind how this works in the physical world. This is just a mechanism that appears to at least describe the properties of quantum mechanics in a really accurate way. It doesn't mean it's correct. It's just an interesting interpretation.
Droplets like these are known as walkers. The bouncing oil drops have been known about since the 1970s, but only recently has it been discovered that you can use these little droplets to replicate many of the strange phenomena of quantum mechanics. Now, obviously, this is not a quantum system. The droplets are about 1 millimeter in diameter, but you can think of the droplets like quantum particles, say electrons. One experiment that captures the key features of quantum mechanics is the double slit experiment. If you send a beam of electrons at two narrow slits, well, the electrons, rather than behaving like particles and ending up in two clumps behind the slits, they produce an interference pattern, even when you send each electron through one at a time. With walking droplets, the pilot wave goes through both slits, interfering with itself, while the droplet only goes through one slit. The droplet doesn't move in a straight line, though. It's deflected by its interaction with the wave. The resulting distribution of where the droplets end up looks very similar to quantum double-slit interference patterns. Or take tunneling. In quantum mechanics, it's possible for a particle to get through a barrier that it wouldn't classically have enough energy to get over. This has been demonstrated with walkers by creating a shallow barrier under the surface of the oil. Usually the barrier reflects the pilot wave and its bouncing droplet, but in rare cases the droplet does cross the boundary. And the probability of the droplet crossing the barrier decreases exponentially with the increasing width of the barrier, just as in quantum tunneling. Perhaps the most surprising thing about these walkers is they exhibit quantization, just like electrons bound to atoms. Here the walker is confined to a circular corral. The droplet seems to move around randomly as it interacts with its pilot wave. The complex interaction between the droplet and the wave leads to chaotic motion of the droplet. But over time, a pattern builds up. This is the probability density of finding the droplet at any point within the corral. And it looks very similar to the probability density of electrons confined in a quantum corral.
Now you got to admit, people, that is pretty cool. All right, let's just leave that for now and get back to the presentation. I hope you appreciated that. I think that's a pretty amazing experiment. At least it's fun to watch, but I insist don't take it seriously. Okay, this generally is more our attempt to try to make nature conform to our expectations. Surely it's not the correct interpretation, but it's provocative to say the least. So let's leave the interpretation aside now for good. What we're going to do is shut up and calculate. And so let's just talk about what quantum computing is now. We've finished talking about the bizarre nature of quantum physics. Now, how does this apply to what we're doing here? So here's a nice map of computing science. So there's a huge area about theoretical science, computing science, computer engineering, of course, and then all the applications. We tend to be in these areas. There's engineering. And so those are all the different regions within each domain. And where are we? Well, we're right there. That's us. Quantum computing is a small little chunk of theoretical computing science. And so today, our classical computers, both in theory and practice, so theory is Turing machines, computational complexity, we're going to be talking a fair bit about that. You're going to have guest speakers coming in from our theory group. And practice, these machines we're using right now are based on classical physics. And so, but that's not, it doesn't have to do, the computations are done classically. Streams of electrons. We don't have to describe any quantum phenomena here. And it's limited by locality, meaning that if something happens here, it affects something over here according to the special theory of relativity. Meaning things don't travel faster than the speed of causality, which is incidentally the speed of light in a vacuum, 186,272 miles per second, or almost 300,000 kilometers per second. That's the ultimate speed limit of the universe. It cannot be exceeded, so as far as we know. Let me ask you something, people, just for fun. Is time travel possible?
You can travel forward in time.
Very good. Special relativity allows travel into the future. That's correct. A lot of people don't know that. I mean, I could take off on a relativistic flight to Alpha Centauri, the nearest star. It's 4.25 light years, well, call it 4.5 light years away. If I accelerate to 99.999% of the speed of light, go there, take a few pictures and come back. Round trip for me is 9 years, correct? No, not 9 years for you. I'll come back 9 months older and we'll be closer in age because I took a different shorter path through space-time than you did. Anyway, it's a fun tidbit. That's what we mean by locality. It means that things have a local influence. Something happening here cannot affect something on the other side of the universe, or can it? Also, things happen one state at a time. Our finite state machines are sequential. You know, that's what we mean with classical computing. Whereas with quantum, we have this funny superposition of states, not just a bit, but a superposition of basis states like 0 and 1. Interference, you know, the idea that these probability distributions produce both constructive and destructive interference, which is crucial to quantum computing. Crucial, we'll talk about that. Entanglement, which means that you can carry even more information and do rather amazing things with these quantum bits of information called qubits. And of course, because of entanglement, non-local effects. Very strange. We'll talk about that shortly. But one thing people have to realize is that quantum algorithms and quantum computers will not revolutionize computing across the board. There's only a limited class of problems that these things can address. And that's all inherent in the theory of computation, which we'll talk about. So what is quantum computing? This is what I want you to know. It's a relatively recent subdiscipline within the theory of computation, which we've just seen, where calculations are based on the laws of quantum mechanics. Right now, we're using quantum mechanics to build these machines, but we're not using quantum mechanics to do the computations. You all know that, yes? We're using transistors, which are just nothing but switches, and building up switching theory, which is to have a logic gate or a set of logic gates, and you put them in circuits, and you can do simple things like binary addition and half adders, and eventually an ALU, and then you put the whole thing together into a von Neumann machine. All of that is classical, apart from the miniaturization. So, what do we have here? Computing involves algorithms and the theory of computation. So those are the things that you really have to bring into this course. And quantum mechanics, superposition, entanglement, and interference, which are probability amplitudes, we'll talk about that in more detail. Those are the things that we must focus on. But in particular, the theory of computation is where the fundamental limits come from. And that's something like, because we're going to be algorithm intensive here, we really want to focus in on this part, on the theory of computation. We'll be doing that in the 5th week, okay? And we'll have a theoretician come in, and Igor Shakar from our department. Now you notice the quantum, that word detector. This is a website where people have had enough of the nonsensical claims that at least a lot of journalists are making about quantum computers. But the point I'm trying to make here is the theory of computation holds the key to the fundamental limitations of a quantum computer. Our current understanding of physics does not allow us to upgrade the CPU. Instead, what we're trying to develop is a general purpose GPU, okay? And like, QPU, a quantum processing unit. So it's being run by a classical device. And you can see right here a little bit of computational complexity. I'm sure you all know the P, NP, and NP hard class problems. Well, we have a different area called BQP, which we'll talk about eventually. All right. So this is your first reading assignment, Scientific American article by Scott Aronson. Remember Scott Aronson's name? I'm trying to get him to come and give us a talk, but we'll see what happens. I like everything that he does, and the subject, he's very honest. And so this has been emailed to you already. It's something you should read. So fundamentally here in that article, he talks about this, that they use qubits instead of bits. And a qubit can be anything. It can be polarization of a electromagnetic wave, or a photon, I should say. Or it could be spin up, spin down. There's many ways to produce a quantum state. And they're in superpositions, okay? And as said earlier, a superposition is simply a linear combination. Then these superpositions, the bit isn't just 0 or 1. The qubit can be, if you have 1,000 particles, they can be in superpositions from 1 to 2 to the 1,000, which is 10 to the 300, which is more particles than there are in the universe. And we can manipulate all of those in parallel. Now you're starting to see the power of a quantum processor if we can do these things. Thank you, Scott Aronson. That's him right there. All right. When the particle states are measured at the end of the computation, we do some fancy manipulation of the qubit states that are in superposition, and we make them interfere in such a way as with the double slit experiment so as to cancel out all the wrong answers and produce probabilistically correct answers. And therefore, we have to do these experiments over and over again, and there's a lot of problems associated with that. We're not there yet, but that's the dream, to be able to make that type of thing work. So once again, superposition. Notice we haven't said anything about entanglement here, but superposition allows for this incredible amount of quantum parallel processing, if you will. Even though you can't actually see what's going on there, don't forget that before you measure a quantum system, it can do its thing, and you don't know exactly what it's doing. You only know the probabilities. And the moment you make a measurement, the wave functions collapse and so forth. And if you've intelligently organized the quantum circuit in the pre-measured state, it'll produce probably the correct answer. And you just have to repeat it over and over again, and eventually you're there. And so that's what the interference part is. Here is an important slide, slide number 40. I think after this, I'd like to take about a 5 or 10 minute break. Is that okay with you people?
Sounds good.
Yep.
Yes.
I'd like to take a bit of a break. This is an important slide here. The problem of decoherence. This name, decoherence, you should be taking notes. Which slide's important? Well, slide 40 is important. You're going to have to be able to understand that there's this name, decoherence. That simply means I have a quantum state, and it's extremely fragile, because don't forget, any kind of measurement or interaction, if you will cause the wave function to collapse. And so it's a very fragile thing. That's why you have to keep these things at such low temperatures, fractions of a degree above absolute zero, which is what a D-wave machine is. They have these things here in Vancouver. We talked about that on Tuesday. And all they are is big refrigerators. And so you've got to manipulate them in a gentle fashion. And we're not going to even discuss that in this course. What happens before you measure, we're just going to be talking about the manipulations that we can do, but how we actually do it is beyond this course. And so I call that the hardware problem. The hardware problem is that you've got to keep these qubits, in the quantum state as long as possible in order to produce, an effective calculation. Then there's the other problem, the problem of insufficient structure. And what I mean by that is the structure of the actual algorithm, okay, of the problem you're trying to solve. Making algorithms that produce the correct interference may be difficult, okay? That's called the software problem. I call these things the hardware problem and the software problem. What does this mean? That means that, what we'll learn shortly is that there are certain problems that they're very amenable. They have a structure like a periodic structure from which you can produce things like the Fourier transform. And I think, does everybody know what the Fourier transform is? Because we'll be talking about that in about a month. Maybe you should look into it ahead of time. It basically is a transformation on a time series, which allows you to look at its spectrum, okay, its frequencies. So if I take a Fourier transform of a pure sinusoid, it'll just come up with the spike as a spike at the exact frequency of that sinusoid. So, if you have particular structures like that in your problem and then an effect in your algorithm, then you can use that strategically to produce these interference patterns, which give you the correct result. Some problems lack any kind of structure. Now, your first assignment I'm actually going to send to you today. It's just it's a research assignment. There's no mathematics, but it's going to force you to think about what a quantum algorithm really is. There are two very interesting papers. I'm going to stop this right now, stop share, and I'm gonna bring up what I would like to give you. It's an easy, fun problem. You'll see it is. Okay, so what do we have? Assignment 1. Okay. Okay. I think this should do the trick. Can you people see this?
Nope.
Just your face right now.
Okay. Okay. All right. Oops, wrong one. I want you share screen. There we go. So this is your first assignment. And actually, it's going to be due not Tuesday, but Thursday. 2 weeks to do it. I was going to assign it on, yeah, it's going to be the 28th. But anyway, what it is there's these two papers. I've already sent you this one, The Limits of Quantum by Scott Aronson. It's written in 2008. And also, one of the most famous people in quantum computing is Peter Shor from MIT. Actually, you can see his online courses from MIT courseware. Why haven't more quantum algorithms been found? That was written in 2003, 5 years before this one. Now, you've got to read those to at least appreciate the problem of software, okay, that I was referring to you earlier just now. In order to appreciate that problem, you'll be able to understand more fully what a quantum algorithm is and how it's different from a classical algorithm. And that, in fact, we have made so much progress since this, okay? There's a web page you can go to called I think it's called the Quantum Algorithm Zoo. And there's hundreds and hundreds of quantum algorithms now that are out there. And eventually we're going to get to it. But for now, I want you to read these two papers and then use those to make a reasonable retort to these claims of me here that why aren't there more quantum algorithms? Because since then, there's been a lot made, and I want you to figure out why. Does that make sense, people?
Yep.
Yeah.
Okay,
Yep.
that's very simple what I want. All you got to do is just write a paper summarizing the progress that has been made since these two publications. It'll involve understanding the software problem of insufficient structure discussed in this PowerPoint and how we've made progress since then. It's a really great way to get you started in actually understanding how quantum algorithms work so that we can get to that part of the course quickly. Don't forget, it looks intimidating, lots of math, bizarre physics, but just pay attention, listen to me, and I'll tell you what to do. Everybody that's taking this course that puts in a reasonable amount of effort is going to get through okay. Let's take a break. I'll be back in, how about 7 minutes, okay? At 10:30. Everybody good?
Sounds
Good.
good.
Yeah.
Hey,
Yep.
see you in 10 minutes. That's incredible. All right, people. Are we all ready to get going? We're halfway through. Let's okay, excellent. Me too. So let's not forget here, I think slide 40 is very important. By the way, I want to congratulate you all for sticking through so far and trusting me. I want to make you aware of the fact that I'm pretty straight. I'm a straight shooter. That means I'm gonna, if I tell you that it's gonna be, a course that you're gonna get through, I'm not throwing you any curveballs. Believe me, I mean it. So I appreciate the trust. I've noticed that there's, I think we have the full contingent of people here. Very few people have dropped. Don't drop. You'll do well. Trust me. Never trust anybody that says, trust me. Anyway, that's supposed to be funny. So if we can just move on now. Problem of decoherence, problem of insufficient structure. The hardware problem, the software problem. I think that's my own invention. So you're not going to find that out there, at least in those terms. So just make sure you understand that. These are things, I think it's a nice way of classifying things. So here's a red background slide. All right, let's read this. This is really sort of a nice point to summarize. We're faced with the daunting task summarized as follows. We have a hypothetical machine that is limited by how the universe works in terms of what is possible to compute, computational complexity theory. We have to overcome the problem of keeping qubits undisturbed long enough for useful measurements to be made, the problem of decoherence. Manipulating these qubits has to be done in a way that doesn't make them collapse. The problem of decoherence, a big problem still today. We require intelligently conceived algorithms that can manipulate the probability amplitudes, those interference patterns, in such a way, okay, that there's a structure like periodicity or what have you, of the solvable problem. It has to be solvable. You can't solve unsolvable problems by definition. There has to be an algorithm or at least a heuristic under scrutiny such as periodicity and in such a way as to negate all the incorrect answers. Sounds crazy, but we've already been able to do that. Okay, So this point explains why the usual simple introductory programs such as binary addition or hello world, they just can't be done on a quantum computer. Such as okay, so put another way, who would print hello world using a GPU? Okay, do you get that part? A GPU is just a massively parallel way of doing independent operations on, say, the individual independent pixels of an image. And that massively parallel aspect is what makes a GPU such a, I don't know, a beautiful thing in image processing. Similarly, you know, it's designed for a specific thing. This quantum processing unit that we're conceiving is, again, such a specialized processor, or a coprocessor, I should say. So because quantum mechanics is probabilistic, we must repeat these measurements many times in order to have a reliable answer, requiring even more qubits. You know, that's a big problem. So what are we to do? Give up? No, not at all. And we'll see why shortly. Now, since we know what quantum computing is, what is a quantum computer? All right. And so here it is. A quantum computer is best regarded as a specialized coprocessor attached to a classical computer for outperformance in specific types of problems, much in the same way a GPU is a coprocessor for parallel calculations in computer graphics. So we want to develop a QPU, if you will. And given that, here's another assignment, is to watch this video, which comes from CNBC. I can't believe I'm recommending it. I can't believe CNBC actually reported something factual. Maybe I shouldn't say stuff like that. It's 15 minutes long. It's a really, really well done video. So, at this point, you know, in this course, it's a good thing to watch. I recommend you watch it. It'll help you with the rest of the material. Okay? We're not going to watch it here. It's too long. 15 minutes is too long. So here's a slide from a nice site you should go to. Again, I put these links down here so you know where the material comes from. If you like, you can go there, look at it. So we actually have a classical computer controlling the quantum device, and it gives the results back to the classical computer. So a general purpose classical computer controls this QPU, if you will. It produces a bank of individually addressable qubits. And so left to right instructions, unitary transformations. What's a unitary transformation? That's the kinds of things we do on qubits. We'll talk about that shortly, next week, really. Right to left, results of the measurements, right to left, okay? Left to right are the manipulations of the qubits, unitary transformations. We'll find out what that means next week. So it kind of looks like this. Oh boy, here we go. Yeah. What's going on here? Ooh, I see. I don't know why that's there. Never mind. All right, come on now. I went ahead accidentally. Okay, so here we go. That's looking pretty good. So, you know, this is the real thing right here. So you've got a quantum processor sitting there, and that chip goes in here, and the classical control computers control the CPU. That's a real picture. And so broadly speaking, there are three main types of quantum computers. The quantum annealer, like D-Wave systems, right here in Burnaby. And what that is a proof of concept, but it's very limited in its applications. They claim to have tons and tons of qubits, but they're not the traditional qubit we'll be talking about in this course. Analog quantum, we won't talk about that at all here. We'll talk mostly about the dream of quantum computing, which is a universal quantum computer. For example, Rigetti's and IBM's Q Experience. They're real quantum computers that are out there, and it's the future. It's a general purpose quantum computer for specific problems amenable to quantum computing. D-Wave, they're a subset of quantum problems that are currently able addressable by their so-called quantum annealer. We're not going to talk much about that. I'm trying to get one of the D-Wave people to come and talk, give a talk. So far, only 1 qubit's coming. D-Wave, I think they're having a shakeup or something because the common chain, usual chain of command seems to have been broken. I'll figure that one out. You'll have somebody to come and give a talk on that. Now, what does this stand for? Quantum Computing Virtual Machine. There's tons of them out there. So for example, D-Wave has a thing called LEAP. And then Rigetti, they use PyQuil. It's Rigetti Forest. IBM's Q Experience, they have this Python-based assembly-like code called QIS Kit. In other words, Quantum Information System Kit. So Python-based, both of these are Python-based. Good stuff to know about. So here's a nice thing from IBM Research. It shows you the 3 different types. The quantum annealer, the analog quantum, and the universal quantum. We'll talk about this one in due course, but this is really where we're at right here. You can read this one on your own. Make sure you read slides, there we go, 48 and 49. Oh, 48. Make sure you understand this, okay? Slide 48. You can read that on your own. Okay, hope you're taking notes. So here specifically, you can read about IBM's Q Experience. You can read about D-Wave Systems, LEAP, and Rigetti. Those are the, the 2 big ones, Rigetti and IBM. And then, of course, for the problem here of annealing, that's D-Wave. We'll talk about these. You'll understand it better shortly. So let's talk about utilizing quantum mechanics. Now, briefly, this would be sort of, well, let's have a look. So we've got this Industrial Revolution. It began in the early 1700s. And what does it really mean? It means we've learned to mass produce things. And it began in the early 1700s with the mechanical automation period, mechanical textile factories using steam power and so forth. Second revolution 100 years later during the 19th century had to do with hydroelectricity and discovery of oil later on, fossil fuels for sure. And then finally, the one we're in right now of electronics and miniaturization and automation of control. All right. The information age is a stupid term. I don't use it. I don't care about that. It's more for business people. But you can see these 3 distinct periods. So mechanical, production, steam, water. Telegraph, railroad, gas, water supply, sewage. And then finally, production, automation, information and communications technology, internet, everything's digital and so forth. So we can divide it into these periods, which all, by the way, seem to have their paradigm changes within physics. So thermodynamics developed in the steam part of the revolution, electromagnetism developed in the electromagnetic part of the revolution, and then quantum mechanics during the past, say, 120 years or so. And that's the one that we want to talk about in particular right now. And so the 3rd industrial revolution is only based on quantum mechanics. All of this miniaturization, solid state physics, microelectronics, all of this is based on quantum mechanics. And clearly it's correct. The theory is outstanding considering when you look at what we've been able to accomplish with this theory. So we've been utilized quantum mechanics, but to build computers, not to perform the calculations. And you can see the kinds of limits that we're headed for here. We're about to hit a wall on transistor scaling. There's problems. You read about Amdahl's law if you'd like here on returning to trying to make things work in a massively parallel way using classical computers. Energy consumption is a huge issue. We're very inefficient doing classical computations as far as energy is concerned. I know a person who was a film producer, and he overclocked his CPU on his camera so that it ran so hot he had to actually supercool it with liquid nitrogen. So think about that. So what about this? Now, quantum computers perform their calculations using quantum states instead of current flow. Measuring electrons flowing from one transistor to another is classical. When you get the transistors down to the size of, oh, I don't know, atoms now, that's when quantum effects start appearing. Things like quantum tunneling can happen, and I'll show you an image of that some other time. But let's talk about what we mean by state. What do we mean by state when we're talking about, say, computers, classical computers? Anybody? Anybody you want to gander a guess?
Essentially, it's just the program state, so like variables, where you are in the program, etc.
Yeah, the state of the, like in operating systems, we know what a oh boy, I'm getting old. Haven't taught that course in a while. How you define a process, for example, process control tables and stuff like that. Defining, everything, including the program counter, everything about the current state of that finite state machine. So in computing science, that's what we do. We talk about, the idea of having, primitive memory. And so, for example, the current state depends on the previous state in a straight state transition diagram of some kind. But in the hard sciences, it's different. Okay. Well, informally, you talk about the state of a physical system, referring to, I can't read this. Okay. I can't read this. Let's see. I got to do this. I'm sorry. These pictures on the side can't do anything. So a complete description of a state of a physical system is informally referred to as its state. Very informal. But the formal description has to do with an aspect of advanced linear algebra known as functional analysis. Here you can see the mathematics beyond elementary linear algebra. Why? Why do we have to talk about these things called vector spaces? Let's have a look here. A quantum state will turn out to be a vector in a complex vector space. That means not real numbers, but complex numbers. And that transformations on these vectors, which is the whole point of using a vector space as a mathematical framework for describing the evolution of a qubit, well, they're going to be transformation matrices, okay? Like, how that worked in your linear algebra course. You multiply a vector by a transformation matrix, and it's all linear, which means, it either is rotated or it's stretched or condensed. Linear transformation means that there's a specific place where your transformation is just simply extending it along a line. That's called an eigenvector, an eigenvalue problem. Just dust off some of these memories for you. But the point I'd like to make here is that, look at this now. It says a quantum state will turn out to be a vector in a complex vector space, and quantum gates are transformations. And this is very much like if you've had probability theory, there's things called probability spaces. You've heard about this too. It's the same kind of thing. A probability space is simply a space of probability. It's just like a vector space is a space of points that are directed from the origin to those points by a vector. So a vector has length and direction and so forth, and we can operate on these vectors and hence map points to other points using these transformation matrices. And so what I'm getting at here is probability is very important. I'm sorry, I had to put that in there. I hope you find the dark humor in this. It's probably the most intense coin toss I've ever seen. Anyway, probability. Here you can see a very nice book that's put out by the American Mathematical Society. You can get it here if you like. It's up to you. I'm not going to force you to memorize it. But the point is, here, let's have a look at this again. Scott Aaronson says it best. Scott Aaronson says, many people today are under the bizarre misapprehension that quantum mechanics is hard. But he blames physicists for that. Once you take the physics out, quantum mechanics is easy. It's what you would inevitably get if you tried to generalize classical probability theory into these probability amplitudes in which now you can have constructive and destructive interference. And guess what? He's right. It's absolutely true. So you can just forget about all the crazy stuff. Forget it altogether and just think about quantum mechanics as a strange generalized probability theory. And probability spaces, therefore, are not even a concern to us because that's part and parcel of this business. So you can get this from his course lecture notes here. You can have a look at that. That green means you don't have to read it, but it certainly will help you. This was a very important slide. Does everybody get that? I suppose so. Okay, it's very important. This is a milestone slide right here, slide 63. If you forget about the bizarreness of quantum mechanics, you're going to be light years ahead. Just think about probability theory, but a different kind, okay? Let's move forward now. Look at this here. This is kind of interesting. You can see that this fellow Keyes in this reference in 1988 predicted from the miniaturization of microelectronics that computations would be performed at the atomic level by now. And we're getting close to it. One electron could store 1 bit of information. Bit, classical. The energy processed per bit could reach the theoretical lower bound given by the so-called Lowndes principle. And nobody in this class has taken statistical mechanics. It's another physics course that if you're a physicist, you'd know about. It's deriving the laws of thermodynamics from a quantum mechanical statistical point of view. You don't have to worry about it. But how many people have heard of the Lowndes limit? Nobody? Well, it's going to cause us to, I'm sorry? Nobody, I guess. Okay. Well, this is where we want to take a slight little departure into the realm of physics. We have to think about physics. We have to think about what information is. We have to think about, the meaning of information before we really talk about a qubit. And so let's just start by thinking about the so-called Lowndes principle. It asserts that there's a minimum possible amount of energy required to erase 1 bit of information. And it's K is the Boltzmann constant. You don't have to know. You don't have to memorize this. KT log 2, it comes from statistical mechanics. And you don't have to derive it. You don't have to know anything about it except that it's there. That is the statistically lower bound of erasing a bit. A dissipative process in the language of thermodynamics, which means it's irreversible. So there are certain kinds of operations that are reversible and certain ones that aren't. You get the idea here? What kind of a computation would be reversible? It's one that doesn't dissipate or lose information. Do you see what I'm saying? So in other words, a bijective function is what you're looking at here. One, it has a one-to-one correspondence between input and output. So for example, the NOT gate, you think that would be reversible? Sure. But the AND gate wouldn't. You'd have to turn it into a reversible circuit or gate in order for it to work. Let's have a look here. So our preliminary summary, what we've learned up to now, is that quantum mechanics is extremely accurate, but we don't really get the interpretation part. So what? The process of miniaturization has taken us down to the quantum level where now we're starting to run into problems like quantum tunneling. Simply explained, quantum tunneling is that you have this wave function, which is a probability distribution, and there can be a barrier that the wave function slightly penetrates. And so there's a finite probability that the particle can actually appear upon wave collapse on the other side of that barrier. That is all it means. Oh, and also the wave function description explains what entanglement is. It simply means I have one wave function describing 2 particles. That's what entanglement means. So you can produce a pair of particles from, say, what is it? positron electron annihilation, which will produce these photons. There's other ways of doing it. A photon will produce a pair of particle, antiparticle pair, and they have to have the same conservation of momentum and spin and all those things. So the original wave function now is distributed over, it's still one wave function over two particles. That is what we mean by entanglement. So anyway, back to this, chip manufacturers tend to go to great lengths to suppress things like quantum tunneling. But instead, here we go, listen carefully, why don't you try to work with quantum effects? And that's what we're doing now, to enable further miniaturization and to apply them to the actual act of computation. And so in certain kinds of problems, we'll have this enormous speed up, enormous because of superposition. But let's think about information now. The Launder limit gives us pause, okay, to think about what we mean by information. What is information? Let's have a little talk about it. All righty, let's go down the rabbit hole then. So, is information physical? How many people say yes? Oh, this is silly over the internet. Let's just forget that part. So what is information and is it physical? A lot of people are starting to think that information is more fundamental than energy, which is kind of strange. If you've ever heard of Maxwell's demon, you have now, and you're actually responsible for it. Your homework, it's informally assigned, is to understand the connection between information and entropy. Entropy is a measure of disorder. Knowing the story of the Maxwell demon, the second law of thermodynamics, and the Launder limit, those things are all connected in some way. So I'm just saying it's not due, but for the midterm, when I say homework, that means this could appear on the midterm or final exam. So hopefully that's a little bit of incentive. There's a good paper here, and there's a nice little video that's an hour long. I don't know, you can read that or you can watch that if you like. I don't care what you do, but understand what this means right here. What is the story of the Maxwell demon? And that is James Clerk Maxwell, who invented electromagnetic theory as we know it. Are there any questions about this? So we always begin by thinking about Maxwell's demon. You can read about it on your own and understand this homework statement right here. Okay, not tomorrow, not by next week, before the midterm. So they're a network. This comes from the Stanford Encyclopedia of Philosophy. It's an outstanding source. There's a network of related concepts of information with roots in various disciplines like physics, math, logic, biology, economy, and the study of knowledge. And there's two central properties. Information is extensive. That means it's additive. Combination of two independent data sets with the same amount of information contains twice as much information. And information reduces uncertainty. The amount of information we get grows linearly with the amount by which it reduces our uncertainty until the moment that we received all possible information and the amount of uncertainty becomes zero. Two nice classical concepts. Entropy, the entropy of a discrete random variable, is the measure of the amount of uncertainty associated with that variable. That is fundamental to understanding information. Again, entropy of a discrete random variable is the measure of the amount of uncertainty. So you can see how thermodynamics and information are very intimately related to each other, at least in terms of Claude Shannon's information theory. Anybody with a degree in computing science must know about Shannon's information theory. So if you don't now, it's a good place to start. And this has to do with what's known as the Boltzmann entropy. I'm not going to make you responsible for that. Okay, don't worry. But the Boltzmann entropy is the traditional form of entropy as the second law of thermodynamics states it. So here, putting it simply, here's Launder. When a system loses information, that information is transferred to the system surroundings. Boy, does that sound like energy? That is, the entropy of the surroundings increases, according to the second law of thermodynamics. According to this law, the more disordered something is, high entropy, the more information we need to describe the randomness. Slide number 75. Excellent slide for you to study. Make sure you understand this slide. Any questions?
Yeah, so in the second line, it says the entropy of the surroundings increase when the system loses information.
Mhm.
So I'm having trouble conflating the first two lines. The
Okay,
system-
okay. Let's think about the second law of thermodynamics. Well, the first law is conservation of energy. Okay, energy can't be created or destroyed. It's just a postulate. It's one of those things that's impossible to prove, but we've never seen it violated anywhere. Proving it would require believing that your devices that you're using to measure in philosophy do abide by the circular argument by the first law of thermodynamics that you're using to try and prove that it's correct. So anyway, there's a bit of faith there. The second law, however, is the state of entropy, or the state of randomness in the universe. Well, in any kind of isolated system, the entropy either remains the same or it increases. The reason why things become, well, the origin of life appears to violate the second law of thermodynamics, because clearly the entropy increase means there's more disorder, but life is extremely ordered, very complex. And in fact, Heisenberg called life negentropy, negative entropy. But the whole thing is it requires a certain kind of a chemistry of activation energies to make it work. But the most important thing is energy going in. Energy is required to create order. Energy is required to go against the second law. So life is the entropy is at the expense of the increased entropy of the sun. That's really fundamentally how that works. But so if you're going to do some kind of a thermodynamic process, if you've learned the basic physics, you've heard of the Carnot cycle for basic thermodynamic devices, basics of how an engine works and the efficiency of a thermodynamic engine. You know that there's going to be losses. There's nothing you can do about it. And so energy is conserved, but it's gone into these different forms like heat dissipation and so forth. And that's the second law. It just basically states that you're going to lose energy dissipating into the system. And the same thing can be said about information. You can send a signal and it may not be, if you lose that information, then the entropy of the surroundings has to increase because you've thrown in energy into the system in a loss of certainty, if you see what I'm saying. Let's look at this. When a system loses information, that information is transferred to the system surrounding in a thermodynamic sense. And so if you think about the relationship between information and entropy in a Claude Shannon sense, the entropy of the surroundings has to increase as energy is being lost from the system. Does that make sense?
Yeah.
More or less?
Yeah.
There's more coming up. Here, let's have a look at the next slide. So anybody that studied this, has anybody seen an equation that looks like that when studying information theory? Okay, let's go back here. Slide 75. Just think about the relationship between energy and information. Okay, let's read this again. It's so important. When a system loses information, that means, if you're sending a signal, you may lose, a few bits. We do that in classical computing all the time. We always have these error correction codes to, take care of this loss problem. Information just simply gets lost and it's irretrievable. Just like energy is lost, dissipated to the system, you can't get it back. Why do I keep looking at that speaker? Sorry about that. So the entropy of the surroundings has to increase by the second law of thermodynamics. The entropy of a isolated system either stays the same or increases, unless you start putting energy into it, in which you can cause complexity, raise complexity, and therefore decrease the entropy. So according to this law, the more disordered something is, high entropy, the more information we need to describe it. That's the relationship right there between entropy and information. And I'm talking to that speaker because was that Connor that asked that question?
No, it was me.
Oh, okay. Marco?
Yes.
Yeah, your voice is really coming through on that one speaker, so that's a little odd. Okay, thank you for that. That was good. So, oops, wrong way. So here, the only mathematical function that unifies these two intuitions, I'm talking about these, extensiveness and reducing uncertainty, is this minus logarithmic function, all right? This is an introduction. I'm not going to ask you about this on a test yet, okay? We'll talk more about it if it's necessary. I'm just introducing you to the theory of information. Okay, so uniting these two intuitions right here, being extensive and being reducing uncertainty, is this minus logarithm. Okay, now what do I mean by that? This relationship defines the amount of information we get when we select an element from a finite set A. Clearly, the logarithm is the only function that satisfies additivity. Okay, this part right here, the additivity constraint. And other things too, like monotonicity, normalization constraints, and other things that you would think about in the theory of information. So consider this part a bit of a digression, okay? And what do I mean by that? Is information physical? That's what Landrer was trying to talk about. He said yes, but there's still a lot of debate. So for example, here, information is formally related to entropy, the second law of thermodynamics. Not energy, entropy. Computers must obey the laws of physics, obviously, just like our brains have to. And computing requires energy for altering information. And you can see what I'm talking about here by moving a pebble over. I'm basically defining a state by the configuration of matter. And so, you know, there's some things where I can consider irreversible. I can get, it doesn't require energy. Operations which permute are reversible, bijective functions. Operations which erase or overwrite are irreversible. You must know that. Slide 81. Information is lost and entropy increases. Very important, people. Very important. And if you're interested, you can look at Appendix 2 of this PowerPoint for a proof of that, but I won't make you responsible for it. You are not responsible for that. This is another really great video, Quantum Computing for Computing Scientists. It is it's from Microsoft. It's outstanding. And in fact, we'll be responsible for this next week. Next week, I'm going to use his slides and I'm going to basically talk through them with you, but I urge you to actually go to the website and watch it first. I don't like the font I'm using here. I don't like that font. Okay, there I go. I just love to do this type of stuff. Oh, that looks so much better. Thank you. Now let's wait 5 minutes while this PowerPoint saves. All right. So is everybody good on this part right here? The idea of reversible versus irreversible. Reversible, you have to have a bijective function, a one-to-one mapping from input to output states. That information and entropy are related in an inverse manner. And here, this is a beautiful slide from his Microsoft lecture that we'll be talking about. So you see the identity function as a clear one-to-one mapping. The negation is a bijective mapping as well, one-to-one, but constant 0 and constant 1 are not, right? Because there's not a one-to-one mapping here. Now in matrix form, we can see how it looks right here. Basically, you've got the matrix, which is an operator. That's the identity matrix. And if I multiply any vector by the identity, I get the same thing. And here, this is the inverse negation. And if I apply that, I get the inverse state. And here, the constant 0, that's what it looks like. The constant 1, that's what that looks like. We'll get there. This is just review for you. And so bijective relations are reversible. We'll be focusing on those for quantum computation. All right, so it behooves you to look at this video from Microsoft. Let's talk about superposition and entanglement now. Why is it that they appear to be so powerful? Okay, so there are some theorems. The following theorems describe the limits on manipulation of quantum information. These, in physics, we call them no-go theorems. The big no-go theorem of my research has to do with it's called Cowling's theorem, and that you cannot generate magnetic fields from purely axisymmetric motions. There's a whole pile of these different kind of theorems that apply to quantum information. For example, the no teleportation theorem. A qubit cannot be wholly converted into classical bits. So in other words, it cannot be read. You can't look at a qubit before measurement because it's in superposition. You cannot see it. You cannot measure it. If you do, it'll collapse. The no deleting theorem, which prevents an arbitrary qubit from being deleted. Again, because it's before measurement. The no broadcast theorem. Although a single qubit can be transported from place to place, quantum teleportation, a real thing. We've demonstrated it in the lab. But it cannot be delivered to multiple recipients. We'll get to that. This is just looking ahead. And the no hiding theorem, which demonstrates that conservation of quantum information exists. Quantum information is conserved like energy is conserved. These theorems prove that quantum information within the universe is conserved, just like energy in the universe is conserved. They open up possibilities in quantum information processing. That's what we mean. So that part of the course is done. We've got 10 minutes left. I'm going to go through this really quickly now. This is a slight history. You don't have to read chapter 2. All you need to know is the history I'm providing right here. You know, who's Richard Feynman? You have to know who he is. In 1982, he suggested that analyzing molecules is so difficult for a digital computer as to make it intractable. It's just intractable. For example, here, let's have a look. That's the Schrodinger equation, at least the time-dependent version of it. You don't have to reproduce it. I'm not even going to describe it at this point. It's a partial differential equation. So we understand the mathematics, but here, this partial differential equation, okay, there's no difficulty in actually solving it in order to introduce it to quantum computing. The problem is that there's an intractable combinatorial explosion, even for the simplest molecules, like, for example, the nicotine molecule. The amount of information required to model the relatively simple caffeine model. Did I say nicotine? Sorry about that. Look at this. It's such a relatively simple molecule. It would require a number of bits equivalent to nearly the number of atoms that make up the Earth in order to model this. It is intractable. It's due to superposition and entanglement. So a simple molecule like this is intractable on a classical computer. Hence, that's why people say when we develop these quantum computers, or at least quantum co-processing units, we'll have a field day in designing pharmaceuticals. That's very important, but that's not really why the funding's there. Does anybody know why the funding's there?
Cryptography.
I'm sorry?
Breaking cryptography.
Absolutely, yes. So it's national security. So to overcome intractability, Feynman proposed doing calculations based on quantum mechanics. But this business of intractability naturally lends itself to the next fundamental question. How does quantum computing fit within the theory of computational complexity? And so let's look very briefly. I think this is going to wrap it up right here, this part right here. So the theory of computation is approached through three main subfields. I mean, you've learned a bit of this in Macam. You've learned a bit of it in 225. How many people have taken Physics 309 or Compute 309? That's not good. Okay. This branch was established in the 20th century. Okay, so automata and formal languages. We want to worry more about computational theory, like recursion theory and so forth. Is it possible to formulate a specific problem using the Turing machine? All right. As such, the basic questions of addressed by recursion include: what does it mean for a function on natural numbers to be computable, solvable? Well, there has to be an algorithm. How can problems be classified into hierarchies of difficulty? For example, addition is clearly simpler, innately simple than multiplication. And computational complexity, the big one, okay? The efficiency at which problems can be solved, whether a problem is tractable or intractable. So, you know what a Turing machine is? You've learned about it. It's a model of computation. We're Turing machines, although there's some philosophical discrepancy there. And despite the model's simplicity, given any computer algorithm, a Turing machine capable of simulating that algorithm's logic can be constructed. That's the whole point of this. Now, of course, we need to come up with a quantum Turing machine, which we'll talk about shortly. Church-Turing thesis has a lot to do with Gödel's incompleteness theorems. Says that every physical process can be simulated by a Turing machine and to any desired precision. So the way Church and Turing understood this was as a definition of computation. But we can think of it instead as a falsifiable claim about the physical world. You can think about this as the idea that the entire universe is a video game. You've got all sorts of complicated things like quarks, they make up hadrons and whatnot. But at the end of the day, you've got to be able to simulate it on a computer. The theoretical computing science is pure mathematics, and it is connected to the real world through the Church-Turing thesis. That's from Scott Aronson. That is a really nice description in a nutshell of what we mean by the theory of computation. So here's the ghost in the machine, of course. Quantum Turing machine's an abstract machine as well, in the same light or vein as a classical Turing machine, but any quantum algorithm can be also expressed as a particular quantum Turing machine. So this fella here, Deutsch, in 1985 actually developed the concept of a quantum Turing machine, which allowed us to extend our classical notions into the quantum realm. Here's another paper it's an easy read, it's short, and I've sent that up to you as well. It's a good place to be. But this is the good stuff. We don't have to worry about this. Quantum Turing machines are both difficult and confusing. People use the quantum circuit model, which is computationally equivalent, and they look like this. Here's a bunch of qubits. You've got 4 qubits here. You have these gates, and you have these entangled states with these CNOTs. That's a Hadamard gate. That's an X gate, a Z gate. And that's your measurement. All this is reversible. That there causes the collapse of the wave function. These here are nothing more than matrix transformations on qubit states. We'll get there. Fortunately, we don't have to use this. We can develop all of this on a Python-based language like Puke. Puke? Did I just call it Puke? PyQuil. So, a complexity class is a collection of problems which can be solved by some computational model, given some resource constraints. For example, the complexity class P, that consists of all the tractable problems that can be done in worst case polynomial time by some kind of a Turing machine. Similarly, one may define a quantum complexity class using a quantum model of computation. Okay, so these guys here, Bernstein and Visrani—Visrani's very, very big in the field from Berkeley University, defined the complexity class BQP, bounded error quantum polynomial time. Whoa. As a quantum generalization of class P. We'll talk about that in the 5th week. Loosely speaking, BQP, bounded error quantum polynomial time, contains all decision problems, yes or no, true or false, that can be solved in polynomial time, worst case polynomial time, by a quantum computer. So you can see we're extending the theory from classical to quantum. So there's some details here. We'll talk about this later. I don't want to talk about this right now. This is just being pedantic. And here you can see in the theory of computation, again, from another colleague in England who has agreed to share his notes and his videos with you as well. If you're interested, I'll let you know. Just read this and this on your own. You can see where we're headed. All these quantum computers can do is somehow, in a way that's not well understood, extend the boundaries of tractable problems somewhere into NP space. What's NP space? Non-deterministic polynomial. You should read up on it in basic complexity classes if you're not sure. And I think that's pretty much all we have time for. You should see this video right here, P versus NP and the computational complexity zoo. This is an outstanding video. In fact, I'd like you to watch that for sure for our next video. It is now 11:18. There's no point in going further. The theory of computation. Okay, an understanding of the theory of computation as well as the theory of probability is central to understanding quantum computing. So that's a nice place for us to stop. So with that, I'm going to bid you adieu. If you've had problems with video and or audio, send me an email just saying audio problems, okay, or video problems. Let me know and we'll try and resolve them. I'm going to send out that, that homework, or that assignment number 1, which is simple research, you know, on what quantum algorithms have, the state of quantum algorithms since those 2 papers. Other than that, I'll see you on Tuesday. If you want to set up a Zoom meeting, usually I like to do it after the lecture on Tuesday. Thursday, like today, I'm burned out after doing 2 hours. And so I can't envisage actually holding an office hour right now, if you know what I'm talking about. Tuesday'd be best, but if you want to email me a different time that you'd like to discuss it, or just give me your problems via an email, we can take care of it that way. Are there any questions?
I do have one quick question.
Sure. Okay. All right.
So you mentioned that all quantum operations are reversible. Is that excluding the measurement from the set of operations? Oh, okay.
Absolutely. Oh, the measurement is clearly irreversible.
Yeah.
You know, once the wave function collapses, you can't go back into that. It's over. The whole state, the decoherence problem has happened. I got to turn that speaker off because I'm always looking over here talking to you. Yes, you're absolutely right. That is irreversible. Measurement is irreversible. Well then, all right, people, it's been a pleasure. Stick with it. And on Tuesday, I'm going to give you a really explicit roadmap. You can see right now that we haven't even made it halfway through this presentation. So that's good. That's good. I think we should take it at this pace. The syllabus is definitely going to be expanded, okay? I want to make this enjoyable. I'm not going to run at a really breathtaking or neck-breaking pace. I want this to be fun. And with that, I bid you adieu. Bye-bye.
Farewell.
Farewell. Ciao, ciao. Bye.